Welcome to a demonstration of program DYNACAM, the student edition in particular. I'm going to show you how to use the program to design a simple cam and get you started with that process. So let me move to our brief PowerPoint over here and give you a little introduction as to what we're going to be doing. Usually the first thing that you encounter when you're assigned to design a cam in industry would be the timing diagrams for the machine in question. This is an actual timing diagram of an industrial assembly machine, and I show 5 different events here. There will be many more than that on a typical machine. This is an indexing machine, so we see an indication of what the indexing cycle is, moving pallets along. This also tells us something about the index. I don't care about those today. The thing I'm interested in most is the assembly motions or other kinds of motions that are being created on the machine with the cam systems. This represents one of them. You see a dwell at a high position for about 10 degrees, a fall to 105 degrees. It says it's now in at the nest for placing a part. It stays there until 190 degrees. It comes back out at 285 and dwells at the out position. So this would be a double dwell type motion as described in your book. Even though it looks like there are 3 dwells, this is just the tail end of this same high dwell over here. So it's dwell, fall, dwell, rise, back onto the dwell. This one down here apparently is a double motion, twice per cycle. 360 degrees would be a complete machine cycle. So this is in the middle of a rise at what's termed machine 0, which is just a reference point for all events in the machine when you consider the cycle to start. So this particular follower is in motion. It dwells for a short time. It falls. It dwells. It rises. It dwells. It falls. It dwells, etc. And in the meantime, some grip jaws that are on one of these devices are opening and closing to grab parts. So let's look at something like this one right here as a first example. From that, we would extract that piece of the timing diagram, now looking at a particular cam. This isn't the same order as we just saw. It's just generic. So we have a double dwell situation, a low dwell followed by a rise, followed by a high dwell, followed by a fall. All of that eats up 360 degrees, which represents some time period which will repeat with each cycle. So that's our starting point for the design. The first step is to convert that timing diagram into a set of SVAJ diagrams, as you see here. S is the linearized displacement. We're working in a linear form here to keep it simple. We're going to wrap this around a circle to make the cam, and we'll do that before this video is over. But initially, it's much easier to deal with this in a linear fashion, so we're pretending that the follower is moving straight up and down, and the cam is moving under it. The follower is not shown in this diagram. His displacement, his velocity, which is its first derivative, acceleration, the next derivative up, and jerk, the next derivative after acceleration. So we're going to create these in program DYNACAM. And to do that, I've just made up this simple example. We're going to dwell for 60 degrees, and then we'll lift the follower through an inch of motion in the next 120 degrees, dwell again for 60, then fall back through the same inch in 120 degrees, and we'll run this thing at 100 RPM, which is 10.467 radians per second. So now I want to draw that diagram for you on the paper so you have a better idea as to what's going on. I've already set it up by drawing the axis, which is our timeline, if you will. I show it denoted in degrees, but you realize this, of course, is also convertible to time depending upon your speed. Over the first 60 degrees of motion, we're dwelling at the low position, so I've added a red line to that to indicate that we're dwelling. And then we later on want to dwell up here between 180 and 240. That's our 60-degree high dwell. And we want to get from here to there with some kind of a rise function. And that's the first challenge to an engineer in designing a cam, is what mathematical function should I choose for this motion? And as you've been probably talking about in your lectures on cams in the course, that choice of function has a big effect on a whole host of factors, not insignificant among which are its dynamics. So we're going to move now to program DYNACAM and put in this information, and then I'll show you how to put some various mathematical functions in that cam. This is the screen that you will see when you first run DYNACAM. Hit the Start button to get it going. This disclaimer says it's used for use by students and teachers for educational purposes only. Your name may or may not appear automatically here. If you're on your own computer, I will grab it from your computer and place it there, but if you're on a school computer, it probably won't show up. But you can type your name in, and that will annotate your plots, etc. You can type any name here you would like to have for annotation of your plots as a project name, and it also will serve as a name of your disk files that you will send to the disk. Design number I default to 1, and I will increment it every time you change your design and help you keep track of how many changes you've made. You have to agree to abide by the terms of the student license in order to proceed, and if you do, you'll end up at this home screen, as I call it. Initially, there are just 2 buttons available when you first come in, the SVAJ button, which is the one we're going to use, and the Quit button. There's also help available on this drop-down. I'm not going to bring this up now because I'm going to be your help screen today. But you can get help on various of the menu items, and you can get help on various of the buttons. And you also can bring up a user manual from the web, assuming your machine is connected to the web at the time. So let's proceed to do our little example. I'm going to go to the SVAJ screen. If you've seen the tape on the 4-bar program, you know that yellow boxes in these programs are for input and the cyan are for feedback to you. So I can type in any yellow box, and the first thing I'm going to put in is the speed of this thing, which I think was 10.467 or something like that, radians per second. Now, number of segments, those are defined by our timing diagram, and you recall that we had a dwell followed by a rise followed by a dwell again, a high dwell, and then a fall. So that's 4 events, and each of those is a segment. So I need 4 segments for this particular timing diagram. And when I put in the 4 there, I open up 4 lines over here for input. If we go back for a moment to our diagram, we can reinforce that idea and also show you what these betas are. The program's asking for the betas for each of the segments of the cam, and I've drawn them in here. They're the delta angles over which the event occurs. We said the first dwell was 60 degrees, so its beta is that number. The next thing rises over 120, so that's our beta for that. Then beta 3 is 60, and beta 4 is 120. And we're going to call these low dwell, rise, high dwell, and fall. Okay? So back to the program now. We'll put those numbers in. So the first item was 60 for the dwell, followed by 120. I'm typing these in from the keyboard. I'm using the tab key to move to the next box. You could also go there with your mouse if you wished. I could just click on the box down here. Move the mouse out of my way. 60 for the next one, and then 120. And those obviously have to sum up to 360, and I'm summing them on the fly as you go. If they don't sum to 360, it's going to bark at you and make you fix things until it comes out that way. Next thing I want to do is to select the motions for each of these segments over those betas. And the first thing we said for this example was to be a dwell. We then wanted a rise. I can use the drop-down menu, or I can type in here the first letter of the word. So if I type D, it'll pull up the dwell. And if I type F, it'll pull up the fall. That's the same as if I had dropped that menu down and grabbed the fall off of it. A dwell is a dwell is a dwell. So if you choose a dwell, there's nothing else to pick over here in terms of type of program. But for the rise, you have quite a variety of things you can pick from. You could pick a modified sine, a modified trapezoid, a cycloid, some other possibilities. I would not use a simple harmonic motion because that has infinite jerk and discontinuous acceleration, which does not obey the fundamental law of cam design, as you should know from reading your Chapter 8. A double harmonic is not a choice for a double dwell, so there's only a few I can use here that would be useful. That one is not one. Let me put back something more reasonable. Modified sine would be a reasonable choice here. And just to be different, I'll take a modified trap on the fall, for no other reason than to show you both. Now, the next thing to do is to tell it what the excursion is, what the motion is. And we said we were going to dwell at the low dwell initially for the first 60 degrees, so that's at 0. And note that in the S diagram, regardless of how big your cam may end up being, I'm always starting the displacement at 0 and moving to some larger value, or conversely starting at some value and coming down to 0. The point being that I'm going to go either from or to 0 or possibly through 0 with my S numbers. Now for the rise, we said we wanted a 1-inch total rise, so we're going to go to 1 there, and it fills forward as far as it can. If I put it at 1 at the top of the hill and it knows there's a dwell there, it'll keep it at 1 for the dwell, and it's now about to come down the hill on the fall, so the 1 has been put there for me, so I'll bring it back to 0. So now I have all the information there necessary to calculate, and you may have noticed that these buttons were dimmed before and now they're not, because once you have complete information in the row, I wake up the button so you can do a calculation. If I hit that, it calculates the dwell, which is just a case of putting zeros in all those buckets. That's pretty trivial. This one goes and calculates the modified sign for the SVA and J for me. Looks like nothing happened, but I can see what happened by hitting the plot button, and this is what it did. There's my S curve. There's my velocity curve. There's my acceleration curve, and if you've read your Chapter 8 about modified sine, you should recognize that as such. It's got a rather rapidly changing quarter sine wave up to the peak at the 1/4 point there, and then a cosine down to here, and then another quarter sine to there. There's the jerk curve. Jerk is discontinuous, which is acceptable, but the acceleration is continuous, which is required. It's matching up with the dwells. We'll see that in a second when I plot all of them for you. So any one of these, once you calculate it, you can plot it. And when you're done with that, you can hit the next button. And I bring you to this screen, which says resulting boundary values at the interfaces. Now, I've arranged this screen so that I can check students' work very easily to see whether they've obeyed the fundamental law of CAM design. And that means you can check it before you hand it in to your instructor. What I've done is I've grouped the values of S, V, A, and J at the beginning and end and beginning of each segment together. This is segment 1, first end, second end, beginning, terminus. This is segment 2, beginning, terminus. So these two are the same point. The end of segment 1 and the start of segment 2 are the same physical point. They're at 60 degrees in this case. I have to have the same value of S, V, and A to obey the fundamental law. I don't have to have correspondence in the jerk. So this is acceptable, and so are these. If I see any discontinuity here, any difference in numbers, I know that somebody has made a mistake, and so do you. All right, we've now presumably calculated our SVAJs, and we can go look at them by going to the plot button. And again, if you've seen the 4-bar tape, this is the same selection of plots that's in that. If you haven't seen that tape, I'll give you a very brief description. Here's 4 plots on the same screen, and we've asked for the SVAJ, which is all we have available at the moment. And now we see the whole interval from 0 to 360. And you can see the dwell at 0, followed by a rise to the 1 inch, in this case, dwelling at 1 for 60 degrees, falling back the 1 inch over the last 120. The circles drawn here can be turned on and off with a switch down here. I suggest you probably want to leave them on because they're going to show you whether you have a problem. Look down here at the jerk. There are 2 circles at the same value. This indicates there are 2 values simultaneously indicating a discontinuity. So this is acceptable in the jerk but would not be acceptable here in the acceleration, the velocity, or the displacement. So I want to see 1 circle at each of these interfaces down through the acceleration. Here's the characteristic shape of a modified trap acceleration. Here's the characteristic shape of a modified sine. The velocity is distinct in the case of the modified trap because of the straight line sides. The velocity here is a harmonic shape. The displacement functions look not at all different. Once you've integrated out these differences, they look the same. So 2 integrations is sufficient to smooth out the differences. You really can't tell by looking at the displacement what kind of a function you have. You have to look at the higher derivatives. So we now have succeeded in doing an SVAJ plot. And we could go back, if we wished, and change some of these to different choices. Let's take a cycloid there instead of a modified sine, and let's take something else down here. Well, let me show you a bad example just to reinforce this whole issue of the fundamental law. I'm going to pick a simple harmonic on this one. I'm going to recalculate, leave this. Now look what we see here. The acceleration between the dwell, which is segment 3, that's the high dwell, and the fall is discontinuous because I've chosen an inappropriate function. The simple harmonic motion does not give me doesn't obey the fundamental law. And when I go to the next screen, I just hit the next button there. It's reminding me of this. I'm telling you there may be a problem with your CAM design. One or more of your boundaries is discontinuous. And I give you the numbers. Well, S and V, are perfectly fine. But this shows you a discontinuity between A values. And you can either say, okay, I don't care, and proceed, or if you cancel, you'll go back a screen and you can fix it. I'm going to proceed to show you the point as to why this is bad. But recognize the fact that I would not use this function in a real CAM. If we go to the plot screens again, and I bring up this for-plot business, now look at the acceleration here. Now there are 2 circles showing. That's a flag. The other circle didn't get drawn because it's actually over here. You can see them over here. This is the same point as this, right? 0 degrees and 360 are the same point. This is a red flag that something's wrong with your design. Acceptable in the jerk, but not in any of the lower derivatives. So I would reject this design and go back and change it to something else. Now I want to show you how to do something better than either of those that I've shown you, and that will involve polynomials. So I want to return to my PowerPoint for a moment, where I will set that up. If we can switch to that screen, I will have to do that over here by hiding this and bringing my PowerPoint back up and reactivating this guy. That's where we left off, so let's move to the next screen and talk about polynomial CAMs. So I describe polynomials as the chameleons of CAM design. They allow me a lot of flexibility in choice of CAM functions, the shapes and the derivatives and that sort of thing. I can use the standard functions such as modified trap, modified sine, but I also can do some better things in many cases with polynomials. So that's what I want to show you now. We're going to go back to DYNACAM. And I have to do that right here by switching my screen. So we're going to hide this guy, bring DYNACAM back up. I'm going to go back into SVAJ, and this time, instead of picking a rise, I'm going to pick a polynomial. And that automatically changes this box over here to polynomial, since you've already made the choice. And it also wakes up the calculate button over here because I'd have to recalculate. The dwells I'm not changing, so they've remained as was. So if I hit the calculate button over here now, I move to a new screen. Now to explain what this screen is asking for, which is boundary conditions, I have to go back to our little pad and show you another diagram. So here we are back more or less to square one with a representation of our timing diagram. So this is going to end up being S. This will be our V, this will be our A, and this will be our J when we're all done. Here's our dwell for 60. Here's our rise for 120 in this case. Here's our high dwell for another 60, and here's our fall. And this time I want to make them polynomials. Well, to create a polynomial, I have to define the boundary conditions, and the boundary conditions are the values at the extreme ends of the polynomial and possibly also someplace in the middle of the event. I'm going to talk first about the rise, going from 0 to 120. The fundamental law of CAM design, you should recall, says you must have continuity through the second derivative, i.e. acceleration. If I draw on here what the velocity is during the dwell, it should be obvious to you the velocity is 0, as is the acceleration. So during those events, which bracket the rise rather here, in our case, I have 0 values. Well, in order to maintain continuity, i.e. obey the fundamental law, I have to have a value of my displacement rise of 0 at that point to match this, and I have to have a rise of, we called it 1 for this example here. So there are two boundary conditions that I must input to get my polynomial. The velocity must match as well. That gives me two more boundary conditions. 0 here. This would be 0 when beta is 0, and this would be 0 when beta is 120. Remember that the beta 2 was 120 degrees for this particular segment. In like fashion, the acceleration has to be 0 at both. This gives me a set of 6 boundary conditions which can be expressed in little mathematical notation. You know, when theta for this segment is 0, then S is 0, V is 0, A is 0, and when theta for this segment is equal to beta, which would put us here, then S is 1, V is 0, S is 0. Those are my 6 boundary conditions. Now, if I have 6 boundary conditions, that should give you a clue as to how many terms in the equation I'm going to need. Back in DYNACAM, I'm going to tell it that I want 6 boundary conditions over here, and when I do that, it will wake this other part of the screen up. I will bring over the values that you put in on the previous screen, which are the first 2 boundary conditions. S is 0 at the beginning and 1 at the end of my beta. Here's my beta numbers up here. Actually, this is beta over here. Local theta is within the segment, so that runs from 0 to 120. The global theta is from 60 to 180. So global refers to the angles over the entire cam, and local refers to the angles within the particular segment. I'm always calculating my mathematical function within the segment. I end up with what's called a piecewise function with all these segments joined together at their ends. To put the rest of the boundary conditions in, I have to move to the appropriate box and tell it I want 0 at the beginning of the segment in velocity and acceleration, and also in at the end when theta is equal to beta. I want 0 velocity, 0 acceleration. Those are my 6 boundary conditions, and when I've completed those, my next button will come alive, allowing me to proceed, and I'm keeping track of how many you've put in. So when these two numbers match, number of conditions requested and number selected, then you can get out of this screen. And when you do, this screen comes up to tell you what you have for a polynomial. So what I've done is solved 6 simultaneous equations. As you can see in Chapter 8 of your book, I do this exact problem in there as an example, not with these beta numbers necessarily, but with 6 boundary conditions, which gives you what's referred to as the 3, 4, 5 polynomial. It gets its name from the fact that the first 3 coefficients turn out to be zeros, and I'm left with coefficients on the 3rd power, 4th power, and 5th power terms. And you know that your highest power will be 5 because you chose 6 boundary conditions, which gives you 6 terms, or 6th order. The first term is 0th degree, and thus the highest term is 5th degree. That's discussed in your chapter. All right, let's see what that looks like. If I go to the plot screen, the displacement curves will always look the same because the integration smooths their differences out. Velocity looks not unlike some you've seen before. Looks a little bit like the cycloidal velocity. Here's my acceleration curve. That's where you can see the differences. This is a 3rd degree polynomial. This is a 5th degree up here. Differentiate, you get a 4th degree. Differentiate again, you get a 3rd degree. So this is a cubic. Differentiate again to get the jerk, and you have a 2nd degree curve, or a parabola in this case. And that does look, in fact, like a parabola. It's discontinuous at the ends, but that is something we accept for various reasons. But we cannot stand the discontinuity acceleration. So this is an acceptable design. For the fall, I'm going to do something a little bit different. If we can go back to my overhead picture here, a diagram of all of the functions. The 6 boundary conditions that I chose for the rise are the minimum set for this particular case of a double dwell that will satisfy the fundamental law, which says I must have continuity up through acceleration. But I don't have to stop there. if I want to have a smoother function, I can add more boundary conditions. So let's suppose that I ask it to be 0 at the beginning and end in the jerk function in order to match the 0 value of jerk that is present in the dwells. So what I'm going to do now is force continuity through the third derivative, and we'll see in a moment what advantages and disadvantages that creates. If we come back to the program now, I'm going to put in now a total of 8 boundary conditions, since I've added 2 more, and I'll type them in to the respective boxes, zeros all. And when I have the 8 in, when I hit the next button, I solve the now 8 simultaneous equations to get the 8 coefficients, and they are labeled 0 through 7 because my first term has degree 0. And since this is a fall, the 0th component, or the DC component, does have a value here, 1, because I'm starting at the top of the hill at 1. And the only others that have non-zero coefficients are the 4th, 5th, 6th, and 7th degree terms. That gives this the name 4, 5, 6, 7 polynomial, which is also described in Chapter 8 of your book. This panel, which I didn't mention the last time we were here, is reflecting back the boundary conditions that I put in, so you can do a check on whether you got what you thought you asked for here. Now I'm back at the SVAJ screen, and I can plot the function I just created, and here you can see the differences very clearly, neglecting the fact that this is a fall rather than a rise, which we asked for, which of course makes the velocity negative. Just look at the shapes. Velocity looks a little bit like it did before, but it's very flat at the ends here, and the reason it's flat is we told the acceleration to be 0, and we also told the jerk to be 0 there. And when I pin those down, this jerk is the slope of the acceleration, correct? If I tell the slope to be 0, then the slope is 0 here. If the slope is 0, then it starts off with that 0 slope, let's come in from the front end, and then climbs up to a higher value of peak acceleration than I would have had in the 3, 4, 5. By the same token, tying this jerk to 0 at the beginning further flattens the velocity. The flattening increases with each integration. Notice how flat it is at the beginning of the displacement. Virtually nothing is happening over the first 10% of the time here, which means I could actually have increased my time, that is, increased my beta, which would reduce all of the peak values here, and still had the smoothness of the continuous jerk function, but perhaps, not perhaps, I would have some reduced values of acceleration at the peak. That's getting a little bit beyond where I want to go with this introduction, but let's continue. So now I have a new design. Let's go now to our plot screens. On the way there, we see our continuity condition. Notice that between the first dwell and the rise, we have discontinuous jerk, but from the high dwell to the fall, we have continuous jerk because we told it to be so with our polynomial. Let's look at the plot screens. Now, we can see if we look at the accelerations what the differences are. Here's the 3, 4, 5 polynomial. Here's the 4, 5, 6, 7. Here's the jerk for the 2. The jerk is discontinuous for the 3, 4, 5. It's continuous for the 4, 5, 6, 7. That's a good thing for the 4, 5, 6, 7 to be continuous because that will reduce potential vibrations. The trade-off, and there's always a trade-off in engineering, is that I get a higher peak value of acceleration. You can see that by comparing the peaks of these two. Remember, they're rising or falling over the same time period at the same speed. So all other things equal, they'd have the same peak acceleration. But the different functions give me different peak values, different shapes of curves. Okay, I'm going to quickly show you the print screen, which you should have seen from your other 4-bar tape, but it's the same here with some differences. I don't have any built-ins. All you can do is go to mix and match. And as long as you're going to the screen, you can look at displacement, velocity, acceleration, and jerk. And you can scroll through that. We started with a dwell, so those are all zeros. You won't see any numbers until you get down into the body of the cam motion. And we're back on a dwell And finally, we're back to the fall. If I go back, this notice is telling you that the student editions of this program will not print or save any cam contour information. That's to prevent you from making a cam from this. You need the professional version for that. So if you choose to go to a printer, you can't even print the displacement, because from that you could make the cam. Likewise, for a disk file, I only let you look at the higher derivatives. So there's some limitations in this versus the professional version for obvious reasons. Now, I'm going to take us back to the PowerPoint for a second and set up the discussion of the cam sizing. We now have presumably an acceptable collection of SVAJ diagrams that we're happy with. Now we want to make a cam out of this. The next step is to size the cam. This involves several things which result in a determination of the pressure angle function and the radius of curvature function. So I want to describe those briefly before we go and do it in DYNACAM so you'll know what I'm talking about. This shows the cam as it will presumably look when we're done with it. We take our S diagram and wrap it around something called a prime circle, pointed to here. Now, with a roller follower, I'm going to assume I'm going to use a roller follower, which is typical in most cam applications nowadays. The kinematic cam is actually defined to the center of the roller follower. And the physical cam is this red line, which is the surface of the metal. You can think of that as being generated by a cutter of the same diameter as the roller, which is caused to move around this path, which is called the pitch curve, which is the, as I said, the kinematic cam. And we're going to create that kinematic cam in a moment in DYNACAM. If you, again, had the physical cutter chewing away the metal, you would generate this cam surface. The smallest part of that cam surface is called the base circle right here. That's the circle that I can draw within it without going out of the cam physically at any point. And its correspondent in the case of the pitch curve is called the prime circle. So it's the prime circle that we're going to choose in order to determine our ultimate cam size. And around that prime circle, we're going to wrap the S diagram. The S diagram can be thought of if you look at the prime circle right here and this pitch curve with the prime circle subtracted from it, flattened out, is the S diagram. Or another way of thinking of it is if you wrap the S diagram around this prime circle, you get this contour. Pressure angle is defined, as you can read about in Chapter 8, as the angle between the direction of motion of the follower and the direction of the force being applied by the cam to the follower. That force is always along a line called the common normal, or the axis of transmission. It, in turn, that line, the axis of transmission, is perpendicular to the axis of slip. The axis of slip is also called the common tangent, which describes exactly what it is. It's the line which is tangent simultaneously to the cam and the follower. So I can define those lines by geometry, trigonometry, and so forth, and determine what this pressure angle phi is. I'm also concerned about something called the radius of curvature. Now, curvature is a property of any mathematical function, and it's a function of virtually all of the aspects of the function itself. That is, the function plus its first and second derivatives, velocity and acceleration. The radius of curvature that we're concerned with is the reciprocal of curvature. So here's a depiction of what we're talking about. Instantaneous radius of curvature of the cam varies as I travel around the cam. While I want to dwell, it will be constant at the radius of the cam, but where the cam shape is changing, the radius of curvature is changing continuously. I want to avoid either of two situations. The first one is quite easy to visualize, so I'll look at this first. If the negative radius of curvature, which is defined by convention as being concavity, is smaller than the radius of the follower, then it's quite obvious the follower can't get down into the valley right there. And I will not have the follower move in the way that I had intended by choosing the particular function that I chose on the SVAJ set of diagrams. So I want to avoid that situation. I want to keep the radius of the follower smaller than the smallest radius of curvature so that I can get down into the valley. Now, in the other case, I could have the positive radius of curvature become too small, and I then get a condition called undercutting, which is depicted in these diagrams. If you think of the cam contour itself being generated by a cutter of the same diameter as the follower being caused to follow around the pitch curve, then as it comes around a sharp radius on the pitch curve, if that radius is equal to the radius of the follower, I'm going to get a point of stasis right here called a cusp. And I'm going to end up with a sharp corner on the cam, which is going to have very high stresses, and so that's completely unacceptable. If the radius of curvature of the pitch curve shown here in dotted black gets even smaller than the radius of the cam follower, which is this radius right here, then I'm going to cut away material that needs to be there for the cam and still be left with a cusp. So either of these conditions is unacceptable. So what I want is to have the absolute value of the smallest radius of curvature always much larger than the radius of the follower. Or another way to say that, I want to have the follower radius smaller than the smallest radius of curvature. So let's go back to DYNACAM and we'll see what how we create that in the program. If you go to the Size Cam button, it brings up this screen wherein you can choose your prime radius. This is the radius of the circumference of the circle around which you're going to wrap the S diagram. You get to choose your roller radius. That's going to have some effect on this radius of curvature business. And you can also deal with an offset, which I will save for a little bit later. This version of the program only allows you to do a translating follower on a radial cam. The other ones are dimmed out. Those are available in the professional version. So if we hit the Calculate button, for the chosen radius of curvature, which I had previously put in as a 3, we see a pretty acceptable cam. Now, the cam is rotating here clockwise. I can switch that to counterclockwise with this button over here and recalculate if I wish. That would depend upon your particular situation. The cam is going counterclockwise. That's the same as if the roller were going clockwise around the cam, a process called inversion. So if you imagine that you rotate the red follower around the cam, you can see that it will be on a dwell for the first 60 degrees or so, and then it will begin to rise, and then at some point it will begin to dwell at the high position, and then it will fall back to its starting position at the beginning of the low dwell. If I move to the next screen, I see the same picture, and I can still make changes to the prime radius and the follower radius and this thing called offset, but now I'm feeding back to you the values of the pressure angles and also the radii of curvature. And it looks like I have a good cam design here. I have a maximum pressure angle, which is called phi, of 14.5 degrees and a minimum of minus about 17 degrees. And the rule of thumb for translating follower, as you may have read in your book, is about plus or minus 30 degrees. The minimum radius of curvature has been calculated to be, in a positive sense, 2.7 millimeters. That should be inches, because we're working in inches. So these labels have not been properly changed. Ignore those labels. They should say inches. So this is actually 2.71 inches. My follower radius is 1 inch, and that is sufficiently smaller than this 2.71. Remember, the rule was that I want the radius of the follower smaller than the smallest radius of the cam, and that will avoid undercutting. This is about a factor of 2.7 to 1, which is quite comfortable. I would accept as low as 1.5 to 1 in a pinch. I'd rather have 2 to 1 as a comfort factor as the ratio between the radius of the follower and the minimum radius of curvature, in either the concave or the convex dimension. Let's see what happens if we make this prime circle radius smaller. Let's cut it down to 2 and see what happens. It recalculates. You can see now the roller looks ridiculous with respect to the cam. I now have brought my pressure angles up to 20 degrees, which is still perfectly acceptable. My radius of curvature has come down to 1.83. Still acceptable, it's 1.8 times. Let's get even more ridiculous and take this down to 1 inch. And now it won't even do it. Base circles become 0 or minus. It won't even let me do that. So you can see what's happening. I've lost my cam entirely, so this is a silly design. If I go to 1.2, you can see how ridiculous it is. So we want to keep this at a reasonably large value. 3 worked perfectly fine for this example. If I go larger, if I go to 4 inches, for example, the penalty I pay is I have a bigger cam and maybe harder to package. The gain I get is my pressure angles go down and my radius of curvature goes up. I don't think this is necessary for this particular cam. I think 3 or perhaps even 2.5 might work if you wanted to get a smaller package. I have acceptable pressure angles. I've got a very good ratio on my radius of curvature. I think that's probably a pretty good design. Again, this is in inches, not in millimeters. So that gives you some idea as to how to size the cam. This run button will oscillate it for you so you can get a sort of a visual idea of how it works. It doesn't do any more than that. All right. That's about all I'm going to have time to show you today with this program. There's plenty more that it does, as you can see from the other buttons to the right here. But before we part, I will show you how to save your data, which was quite important, since you probably put a lot of work into it at this time. If you hit the Save button, it'll bring up the usual browser window, and you can find your way around on your desktop or whatever, or your disk files, and put this wherever you like. This is the name that was there when we opened the program up. You can change it to whatever you like at this point. I'm not going to actually save this, so I'm going to cancel out. But it would have gone to disk had I said so. Later on, you can, let me back out of here. Later on, you can bring this back with the open command, and you can read that back off the disk. I will say no, I don't want to save it. It'll take you to a browser, and you can search for that and bring it back in, and you'll be back where you started. If you hit the New button, which I did earlier, you will zero out all of the stuff in the buckets. So let's stop there, and I will do another tape later to show you how to use some of these other buttons. I think this has gone on long enough for the moment. So I'm going to hit Quit, and that will take me out of here. I have to confirm the quit, and we'll go back to here and say goodbye. Thank you.